In this video, I want to talk about how action potentials are generated at the trigger zone and how they're conducted down the axon. So I've drawn a soma here in red and one axon in green, and I've blown up the axon to a very large size just so I have some room to draw. Here's our graph of the membrane potential on the y-axis and time on the x-axis. And now I've put a couple of different kinds of ion channels in the membrane of the axon. The first, in this lighter gray, are the leak channels that we talked about when we talked about the neuron resting potential. These channels are open all the time. They're not gated. And I have not drawn any ligand-gated ion channels like the neurotransmitter receptors that occur on the soma and the dendrites. But to talk about the action potential, I need to introduce an entirely new type of channel that I've drawn in dark gray with this little V. And these are voltage-gated ion channels. The membrane of an axon has many voltage-gated ion channels, most of which open when the membrane potential crosses a threshold value. So we've talked about the threshold potential before, and all of these numbers may vary between different types of neurons, but these would be fairly common values. So many neurons would have a resting membrane potential of around -60 millivolts, and a threshold potential of around -50 millivolts or so that I've drawn with a dashed line. And the importance of this threshold potential is that it determines if these voltage-gated ion channels will open. So when there is enough temporal and spatial summation of excitatory graded potentials to get us toward the threshold, here at the trigger zone, at the initial segment of the axon, so let me just draw that we have temporal and spatial summation of excitatory potentials spreading across the membrane of the soma into the initial segment of the axon, the trigger zone. This voltage-gated ion channel has a mechanism to sense this voltage change, and when the threshold potential is crossed, it's going to open, and these are going to be sodium channels. Recall that the electrical and diffusion forces acting on sodium ions are strongly trying to drive them into the neuron. So when this voltage-gated sodium channel opens, sodium is going to flow into the neuron through the open channel, causing that part of the membrane to depolarize from all these positive charges now on the inside. This is going to cause an explosive chain reaction by triggering the voltage-gated sodium channels in the next piece of the membrane. So that more sodium is going to flow in, further depolarizing the membrane and opening the next voltage-gated sodium channel. These voltage-gated sodium channels open very quickly, triggering each other in a wave that rapidly spreads down the axon. The trigger zone has the greatest density of these voltage-gated sodium channels, which is why action potentials usually start at the trigger zone. So many of these voltage-gated sodium channels will open that the membrane permeability to sodium is dramatically increased. This is going to cause the membrane potential, which has already gone from the resting potential to the threshold potential from the graded potentials. But now that all this sodium is flowing in through these open channels, the membrane potential is going to dramatically rise, trying to head toward the equilibrium potential of sodium, which is usually somewhere around +50 millivolts. This rapid increase in the membrane potential values is due to these voltage-gated sodium channels. And this is called the rising phase of the action potential. And in fact, it becomes more positive inside the neuron membrane during this period. That it's the reverse of the resting potential, because normally it's more negative inside than outside the neuron membrane. But now so much sodium has entered that it's more positive inside the membrane than outside. The action potential usually peaks, though, somewhere around +40 millivolts. So it doesn't make it up to the sodium equilibrium potential that's often around +50 millivolts. And the reason for that is that these voltage-gated sodium channels automatically start to close at the higher potential values, so that sodium stops flowing into the neuron. And after they close, they're in a special state called the inactivated state, and they're unable to open at any membrane potential for a brief time. The next thing we see happen to the action potential, basically just as fast as the membrane potential went from the resting potential to the peak of the action potential, it then rapidly descends back toward the resting potential, and then actually goes farther. It goes more negative than the resting potential, and then it levels off. The reason for this part of the action potential, which is called the falling phase, is because potassium starts to exit the neuron. and it does so through a couple of types of channels. The first are the leak channels that we talked about when we talked about the resting membrane potential. Now, a little potassium is exiting through the leak channels at the resting potential, but even more potassium than normal starts to exit because during these parts of the action potential, the membrane potential is positive, so that during this part of the action potential, both the diffusion force and the electrical force are strongly trying to drive potassium out of the neuron, so that more leaves through the leak channels than normally does during the resting potential. The second type of channel that allows potassium to exit are voltage-gated potassium channels. These also open when the membrane potential crosses the threshold, but they're a little slower to open than the voltage-gated sodium channels. So that first, all the voltage-gated sodium channels snap open, allowing sodium to rush in, causing the rising phase of the action potential, and then a little slower, the voltage-gated potassium channels open, allowing potassium to flow out of the neuron, contributing to the falling phase of the action potential. And then the action potential stops falling because now it's more negative inside the neuron again, so there's less driving force pushing potassium out through the leak channels, and also the voltage-gated potassium channels automatically close at the lower potential values, just like the voltage-gated sodium channels automatically closed. But just like the voltage-gated potassium channels were a little slower to open than the voltage-gated sodium channels, the voltage-gated potassium channels are also a little slower to close, so that it takes a little longer for this exit of potassium to stop. And that's why there's this little bit of a longer period at the end of the action potential till we kind of slowly settle back into the resting membrane potential. Because as these voltage-gated potassium channels are slowly closing, the membrane permeability to potassium is returning to the normal amount you get during the resting potential through the leak channels. And as that permeability to potassium returns back to the normal resting potential level, the membrane potential returns to the resting potential. This movement of sodium ions and potassium ions across the membrane, causing the waveform of the action potential, starts here at the trigger zone at the axon initial segment, but then rapidly spreads in waves down the axon. First, there's the wave of depolarization from opening of the voltage-gated sodium channels. So a wave of depolarization rapidly spreads down the axon. But following right behind it, right on its heels, is this wave of hyperpolarization caused by potassium exiting through the voltage-gated potassium channels and the leak channels. So we have the rising phase of the action potential, the peak of the action potential, the falling phase of the action potential, and then this period of hyperpolarization at the end of the action potential has a couple of names. It can be called the after hyperpolarization because it's the hyperpolarization that happens after this part of the action potential. But it's also called the refractory period. Let me just write that down. Refractory period. Refractory period. Right there. And it's called the refractory period because during this time it's difficult or impossible to trigger another action potential in that part of the membrane. The refractory period is divided into two parts. The first part is called the absolute refractory period. And it's absolute because the voltage-gated sodium channels, when they first close, they're in a special state called the inactivated state. And they are unable to open at any membrane potential for a brief time. So that no matter how much excitatory input comes into the neuron, you can't trigger another action potential during the absolute refractory period. The second part is called the relative refractory period. And during this time, the voltage-gated sodium channels have become functional again. They can respond to depolarization. However, the membrane potential is hyperpolarized. It's not yet back to the resting potential. Therefore, it would take more excitatory input than normal to trigger an action potential during the relative refractory period. One important effect of the refractory period is that action potentials travel from the trigger zone to the axon terminals, and they don't turn around and head right back the other direction because the membrane right behind the action potential is refractory. It can't be triggered by itself to send the action potential back the other way.